Hi guys, my name is Stephen Brock. I'm one of the TAs for the course. Welcome to the first tutorial. I'm going to be covering Chapter 2, which is Outcomes, Events, and Probability. Just a little bit of background information about myself. I have a Bachelor's of Mathematics in Data Science from the University of Waterloo. I am currently a student in the Master of Science in Applied Computing program at the University of Toronto, and I enjoy traveling. I've been to New York, Paris, Tokyo, Hanoi. And if you have any questions about what I'm going to talk about in the tutorial, or want to talk about data science or statistics or computer science, or anything really, feel free to contact me. My email is steven.brock@mail.utoronto.ca. And I have office hours on Wednesdays from 3 to 4 p.m. Eastern Time. As an overview of what I'm going to talk about in the tutorial, Chapter 2 is broken up into 5 sections. The first section is on sample spaces. The second section is on events. The third section, probability. The fourth section, products of sample spaces. And the fifth section is an infinite sample space. Hopefully these terms mean something to you, as this was talked about in last week's lecture. But if there's still some confusion or you want a deeper understanding, hopefully this tutorial will help solidify your understanding and clear up any confusion. The textbook we are using is A Modern Introduction to Probability and Statistics. But before I get into any information, what is the importance, or why is Chapter 2 important? Well, events are happening everywhere around us all the time, whether it be associated with weather or sports or just changes to the environment. And Chapter 2 provides us with a model or a way to represent these events. Chapter 2 also provides us with a strong foundation for probability. So Chapter 2 is very important because understanding Chapter 2 will help you understand and learn more complex concepts later on in the course and in your future courses. So Chapter 2 is really essential for success, not only in this course, but also in future courses as well. Sample spaces. So a sample space is a set of elements that correspond to the outcomes of an experiment. For example, consider flipping a coin as an experiment. In this situation, the set HT corresponds to the outcomes of the experiment, heads and tails, respectively. So let's try to model this experiment of flipping a coin. We say that HT is the sample space because it is the set of all possible outcomes of the experiment. And we write this as capital Omega equals HT, where capital Omega represents the sample space. So instead of writing sample space every time, you can use the symbol capital Omega. One way to represent a sample space is with a diagram. So here we have just this rectangle here, and then we see that this whole rectangle is really just the sample space Omega with H and T. Not a whole lot going on right now, but this representation will come in handy later. So consider an experiment of rolling a die twice. So instead of rolling a die just once, we're going to try rolling a die twice. What is the sample space Omega of this experiment? Is it 1, 2, 3, 4, 5, 6? What do you think? Well, hopefully you don't think it's just 1, 2, 3, 4, 5, 6, because we're not actually just rolling the die once, we're rolling it twice. And so we roll the die one time, we write down our observation, and then we roll the die again and we write down the observation. So when we're now considering pairs of observations, instead of having 1, 2, 3, 4, 5, 6, we actually have the first roll followed by the second roll. And so the sample space for this experiment is actually all of the possible combinations of the rolls. So we have, if you roll 1 first, and then a 1 second, or a 1 and a 2, 1 and a 3, then we have a 2 and a 1, 2 and a 2, 2 and a 3, all the way up to 2 and a 6, and all the way up to if you roll the 6 and roll the 6. So interpreting the question is very important, and this is a perfect reminder for not trying to skim the question or dive into any question too fast. It's important to really understand what the question is asking and what is being provided, because if you wrote down the wrong sample space initially, then it's going to take you on a completely different path, and it's going to take you to the wrong answer in the end. So section 2 is on events. So what if we wanted to select a subset of outcomes to group together? So for example, let's just say we wanted the odd rolls of a die or the high rolls of a die. Often when performing experiments, it's not just one outcome, but several outcomes that we want to group together as a single event, or that we want to calculate and perform computations on. So an event is a subset of a sample space. So consider the sample space capital omega is equal to 1, 2, 3, 4, 5, 6, and let the subset O be the event of experiment known as odd outcomes. So O is an example of one of many possible events that people can create on this sample space. Can you think of any other events on this sample space? So in actuality, there's many different events that you can create. And by definition, any subset of the sample space can be used, including the empty set. And we use this symbol to represent the empty set. So another event could be maybe the even numbers, which is 2, 4, 6, or the high numbers, which is 4, 5, 6. Or maybe you just want to have the number 5 as one of the events. Like you're curious, how often is 5 rolled? Or how many rolls is it going to take before I get a 5? Or like how many out of how many rolls, how many 5s, like what the probability of a 5 is going to be, right? So yeah, there's many different events that you can create, and for those of you curious, there are actually 2 to the 6 possible events, and this is because you can actually include or not include each of the elements of the sample space in your subset. So consider rolling a 10-sided die of values 0 to 9. Not sure if you guys have seen a 10-sided die before, but if you ever played Dungeons and Dragons, which is a really fun game, highly recommend checking out if you have the opportunity. You have a die that looks something like this, and yeah, the values are 0 to 9, and it's called a 10D. So anyways, so let E be the event that you roll an even number, and let L be the event that you roll a low number, 0 to 4. What are the elements that belong to both E and L? So when you're trying to construct an event space or trying to figure out what elements are in both of these, it really helps to write down the individual event spaces as well as the sample space that we're working with. So we know that our sample space is 0 to 9, and we know that E is all the even numbers, so that's 0 to 4, 6, 8, and L is all the low numbers, 0 to 4. So we can see by looking at these two sets that the elements that belong to both E and L are 0, 2, and 4. And we call this set the intersection of E and L, and it's written as E, and then this upside down U symbol, and then L. And that's the intersection symbol. Another way to solve this is using the diagram representation that we talked about earlier. So we can draw our sample space, which is this rectangle, and then we can draw our events of the sample space, which are E and L, and then we can fill in the outcomes into our sample space based on which events they belong to. So we have 6 and 8, which belong to E only, and then we have 0, 2, and 4, which belong to the even numbers and the low numbers, and then we have 1 and 3, which are just the low numbers, and then the numbers that don't belong to E or L are 5, 7, and 9. So we can see that indeed the intersection is 0, 2, and 4. Now, continuing on with our previous example, which is when you're rolling a 10-sided die with values 0 to 9, what are the elements not in E? So we're considering all the elements of the sample space that are not in E. And again, when you're looking at trying to construct this event space or this sample space, we want to write down what we know for sure. And we can look at sets that we know to determine what the answer is. So we know that omega is 0 to 9. We know that E is 0, 2, 4, 6, 8, all the even numbers. So all the values that are not in E are 1, 3, 5, 7, 9, all the odd numbers. And we can verify this by looking at the Venn diagram, or the diagram. So we can see that E is this circle right here. And so 6, 8, 0, 2, 4 all in E. So all the numbers that are not in E are 1, 3, 5, 7, 9. So this set actually has a special name. So this is called the complement of E, written as E to the superscript C, because it contains all the elements in the sample space that are not in the event space. So formally, it's all the elements in the sample space that are not in the event space E. And formally, the event E complement is equal to every element K that belongs to the sample space such that the element does not belong to the event E. So we have omega, which is equal to 0 to 9, and then we have event E, which is all the even numbers, and so E complement is all the numbers in omega that are not in E, which is 1, 3, 5, 7, and 9. So hopefully you guys have seen some of these diagrams before. I'm just going to go over them because drawing diagrams is a great tool for understanding and analyzing different questions and sets. So when you're looking at sets or events, drawing diagrams can often be very helpful when you're looking at intersection, unions, complements, just understanding what the question's asking. So the way that we look at the intersection of A and B is it's this overlapping region between the two circles. The union of A and B, it's an inclusive OR. So we have A, the event A, and the event B, and it's anything within those two. And then we have the complement of A, which is A complement. And one of the things we notice is that A and A complement span the entire sample space. So every outcome of the sample space falls into either A or A complement. So there's some important notes. A and A complement cover the entire sample space. So the union of these two events, if we put the two sets together, is actually equal to our sample space. And when it comes to interpreting or just reading some of this notation, A intersection B is sometimes called A and B. A union B is sometimes called A or B, where the or in this case is inclusive. And A complement is sometimes called not A. Some more terminology. So A and B are disjoint or mutually exclusive if A and B have no outcome in common. So that means that the intersection is the empty set, or there is no intersection basically. So we write A intersection B is equal to the empty set. And the empty set is this 0 with a line through it. So we can see here, this is an example of disjoint sets. This is an example of a subset. So A implies B if A is a subset of B. So what that means is if A is within B, like A is completely enclosed within B, like in this circle, then we know that if A happens, B must have happened because A is a subset of B. So if we're in this event space A, then we're also in this event space B. De Morgan's laws. So De Morgan's laws are important to understand / memorize because you can use these as a tool for solving questions. So A union B complement of the whole thing is equal to A complement intersection B complement, and the complement of A intersection B is equal to A complement union B complement. And we can verify these results graphically if we were to draw them out. So we know that if we're looking at the A union B, then the complement is everything that's not in A union B, but in the in the sample space, right? So that's all this blue region over here. And then the complement of A intersection B is equal to the complement of A or the complement of B, right? So the complement of A is everything outside of the circle A, and then the complement of B is everything outside of the circle B, and the overlap is the intersection. So moving on to section 3, which is probability. Probability is used to express how likely an event is to occur. So the probability, for example, of rolling a 6 on a fair 6-sided die is 1/6. We can express the relationship between an event and its probability through what is called a probability function. And the definition of a probability function states that a probability function p on a finite sample space omega assigns to each event A in omega a probability number such that probability of A is in 0 to 1 and the probability of omega is equal to 1, and the probability of A union B is equal to the probability of A plus the probability of B if A and B are disjoint events. The number probability of A, or P of A, is called the probability that A occurs. So what does this mean? Well, property I, or property 1, implies that every possible outcome of the experiment must be in the sample space. So this is important. It means that every time you perform the experiment, with 100% probability, the outcome is one of the outcomes in the sample space. And property 2, or property II, is the additive property, which means that the union of disjoint events is the sum of the probabilities of each event. So when let's just go back for a second, we're looking at these. So if we wanted the probability of A or B, so that it's either event A or event B, well, that's just the probability of A plus the probability of B, because that's how you would add up the chance that it's either A or B. So mathematically, let's use the definition of the probability function to prove that the probability of rolling a die is 1/6. So if we let di be the event the roll is I, for I in 1 to 6, for example, the probability of D3 is the probability the roll is a 3. Since we know that each outcome is disjoint, so we can't roll a 1 and a 2, for example, it has to be a 1 or a 2 or a 3 or 4 or 5 or 6. Then each event is also disjoint because each event is just each outcome. So by the definition of the probability function, we have that the union of rolling a 1 to a 6 is equal to the sum of the individual probabilities. Furthermore, we have that the probability of rolling 1 to a 6 is 100% because every time you perform the experiment, every time you roll that die, it has to be a 1 to a 6. We also know that since the die is fair, the probability of di is equal to the probability of dj for any I and j from 1 to 6. The probability of rolling a 1 is the same as rolling a 2, for example. Therefore, 1 is equal to 6 times the probability of di, or di is equal to 1/6 for I from 1 to 6. There we go. That was pretty cool. So moving on to an example. Consider the sample space of rolling a fair 6-sided die 1 to 6, and let E be the event that an even number is rolled, and let H be the event that a high number is rolled. What is the probability that an even number is rolled? What is the probability that a high number is rolled? What is the probability that an even or a high number is rolled, inclusive? So think about that for a second. Hopefully this kind of comes intuitively, but there's actually some, I guess, like a process that we can follow to compute these values as well. So because the probability of each outcome is the same from 1 to 6, we can calculate probabilities by counting the number of outcomes and dividing by the total possible outcomes. So the probability of A is equal to the number of outcomes in A divided by the total number of outcomes. So what is the probability that an even number is rolled? Well, that's just 3/6, which is 1/2, because in the circle E we have 1, 2, 3 elements, and there's 6 elements in total. What is the probability that a high number is rolled? That is also 3/6, because H has 3 elements and there's 6 in total, so that's 1/2. What is the probability that an even or a high number is rolled, inclusive? So this is a little trickier because now we're looking at two events. We're actually looking at the union of two events, right? So we're looking at E or H, right? So we have 2, we have 4, 6, and we have a 5, right? So together, that is 4 elements, and there's 6 in total, so that's just 4 over 6, which is 2/3. Now, can we come up with a formula to use to calculate the probability of E union H? Because drawing out the diagram is great, and this works really well when we have the probability of each outcome is the same. But what if the probabilities are different? Is there some sort of formula that we can come up with? So in order to come up with the formula, let's examine how we solved it using the diagram. So when we were solving using the diagram, we counted the elements that were in E, H, and their intersection, and we kind of just divided it by the total. But in general, what we were doing is we were looking at E. So if we look at this circle over here, right? We're looking at what's the probability that it's in E, right? What's the probability that it's in H? And we were adding those two probabilities together, right? So, but we were very careful and we actually didn't double count this middle part. So if we look at the probability of E, we have this. And we look at the probability of H, we have this. And if we were just to add those two probabilities together, we'd actually be giving a higher probability than what is actually there because E intersection H would be double counted. So to account for this, we say that the probability of E union H is equal to the probability of E plus the probability of H minus the probability of E intersection H. And there we go. So now we have a general formula. Whoa. Yeah, now we have a general formula that we can use to calculate the union if we know the individual probabilities and the intersection. So this brings up the formula, which is the probability of a union. So for any two events A and B, we have that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So using this, we can look at one of the other facts that we knew about a probability function, which is that 1 is equal to the probability of sample space, right? And the sample space can be divided up into A and A complement. And that's a result that we found on an earlier slide. But this is essentially because every outcome has to either be in A or not in A, right? Because A complement is not A. So it's either A or not A every time, right? It's either a 6 or it's not a 6. It's a 4 or not a 4, right? So we can use that result. And now with this probability of a union formula, we can substitute that to get the probability of A plus the probability of A complement minus the intersection. And what's cool here is that, well, if we look at A and A complement, the intersection between these two sets has to be empty. It has to be the empty set because you can't be in A and not in A, right? So this just becomes 0, and now we get that the probability of A plus the probability of A complement must equal 1. Now, why is this important? Well, that means if we know the probability of A or the probability of A complement, then we can use 1 minus that value to get the other. So the probability of A complement is equal to 1 minus the probability of A for any event A. And we now have an easy way to go from the probability of A to the probability of A complement and backwards. This is another tool that will come in handy. So section 4 talks about the products of sample spaces. How would we express the sample space of multiple experiments together? So for example, let's just say that you had an experiment that involved flipping a coin and then rolling a die. What would that sample space look like? What do you think it would look like? All right, so, well, what do we know? Well, we know that the sample space for a coin is HT, and we know the sample space for a die is 1 to 6. And we want the sample space of a coin and a die. So we're flipping a coin and then we're rolling a die, right? The possible pairs of values, well, that's just a combination of the flips of a coin and the rolls of a die, right? So since flipping a coin does not impact the roll of a die, any possible combination of both samples is possible. Both sample spaces is possible. Therefore, the sample space that we're considering or concerned with is all the values of both of those individual sample spaces. So we have H1, we have a head and then rolling a 1, a head and then rolling 2, tails and rolling 1, tails rolling 2, all the way up to tails rolling 6, right? So in general, we can say for any two sample spaces, omega A and omega B, the joint sample space is now all of the combinations of each of the sample spaces. So this formula can actually be generalized for any number of experiments, including repeating the same experiment multiple times. So continue with this example. What is the probability of flipping a tail and rolling a 4? What do you guys think it is? Well, because each experiment, flipping a coin or rolling a die, is actually independent of the other, we can obtain the probabilities of each of the outcomes by multiplying the probability of each component of each of the outcomes. All right, that was a bit of a mouthful, but essentially what we're saying is that the probability of obtaining one of the outcomes is simply the probability of flipping the coin times the probability associated with rolling the die. So the probability of getting T4 as one of your outcomes, so tail and rolling a 4, is the probability of rolling a tails times the probability of rolling a 4, which is just 1/2 times 1/6, which is 1/12. So moving on to an infinite sample space. Now, consider an experiment where we roll a fair die until we roll a 6. What is the sample space of this experiment? Well, it's in the title, so it could be, well, not exactly, but the section is called an infinite sample space. So, is the sample space 1 to 6? In this case, it actually isn't. So, the sample space 1 to 6, the sample space is actually not 1 to 6 because the outcome of the experiment is the number of rolls to get a 6, not the outcome of the roll. So again, very important to read what the question's asking and really understand what information is provided. So since we do not know how many rolls it will take to get a 6, we say the sample space is infinite, and the sample space is actually a 1, 2, 3, 4. It's basically all the positive integers because we don't know how many rolls it's going to take. So consider an experiment where we roll a fair die until we roll a 6. Now, what is the probability it takes 1 roll? What is the probability it takes 5 rolls? What is the probability it takes n rolls? So let En be the event it takes n rolls to roll a 6, and let P be the probability of rolling a 6. So we know that the probability of E1 is it takes 1 roll to get a 6. Well, that's just P, which is 1/6. Probability of E2 means we did not roll a 6 on the first roll, but we rolled it on the second roll. So what that means is that we want to know what the probability of not rolling a 6 on the first roll is times the probability of rolling a 6 on the second roll. And the probability of not rolling a 6 on the first roll is P complement, or 1 minus P. So thus the probability of rolling a 6 on the second roll is 1 minus P times P, which is 5/6, times 1/6, which is 5/36, since the rolls do not influence each other. Now, consider the probability of, consider E5, sorry, this should be E5. This means we have 4 non-6s and our last roll is a 6. So thus, the probability of E5 is equal to 1 minus P times 1 minus P times 1 minus P times 1 minus P. We have 4 of these times P, which is the probability of getting the 6 on the 5th roll, right? So we have 1 minus P to the power 4 times P, which is 5/6 to the power 4 times 1/6, which is equal to 0.0804. In fact, for any n, we know the first n minus 1 rolls are anything but a 6, right? Because we only got the first 6 we got is the last roll. So the last roll has to be a 6 for the outcome to be n. Thus, for any n, we have the probability of en is equal to 1 minus p to the power of n minus 1 times p, which is equal to 5 over 6 to the power of n minus 1 times 1 over 6. So, does our function satisfy the probability of omega equals 1? Because then it could be a probability function. So where the probability of omega is equal to, this should say omega is equal to 1, 2, 3, and so on. So we have the probability of omega is equal to the probability of event 1, or E1, union E2, union E3, union, and so forth. But because it can't take 1 roll and 2 rolls, or 1 roll and 3 rolls, these events are disjoint, and so we can break it up into the individual probabilities. So we have probability of E1 plus probability of E2 plus probability of E3, and so on. And substituting these for our values, we have p plus 1 minus p times p plus 1 minus p squared times p plus so on and so forth. And by the formula for an infinite geometric sum, we can see that indeed this does give us 1, provided that p is greater than 0. So hopefully you guys remember learning this back in like high school math, working with infinite geometric sums, but I don't know if you need to know this for this course, but it's always good to understand how to derive the formula for an infinite geometric sum. So we actually start with considering a finite geometric sum with n terms, where the first term is p and the common ratio is 1 minus p, such that p is between 0 and 1, and 1 minus p, the absolute value of 1 minus p is less than 1. So Sn, which is going to be our sum, is equal to p plus 1 minus p plus all the way up to 1 minus p to the n minus 1 times p. And then we're going to multiply our sum by both sides by 1 minus p. And we're going to take the difference of this sum. So it's going to be this sum, or this line minus this line. And we get that, we get this right here. And then if we move so if we simplify this and we move the p over to the other side, the negative p, we actually get Sn is equal to this fraction right here. And then the p's cancel out and we get this, given that p is greater than 0, or else we wouldn't have been able to divide both sides by negative p. And we have that S, our infinite sum that we're looking for, is equal to the limit of our finite sum as n approaches infinity, right? So that's the limit as n approaches infinity of this value right here. And we know that since this value is less than 1, that if you raise it to the power of infinity, it actually, if we raise it to the power of infinity, this actually approaches 0. So now this becomes 0 plus 1, which is equal to 1, since that's the value 1 minus p is less than 1. Thus, for an infinite series, S equals 1 as required. So moving on to the definition associated with an infinite sample space. So because our old definition of a probability function required a finite sample space, we need to update our definition. So a probability function on an infinite or finite sample space, omega, assigns to each event A in omega a probability P of A in 0 to 1, such that the probability of omega equals 1 and the probability of A1 union A2 all the way up to infinity really is equal to the sum of the individual events as long as those events are disjoint. So moving on to that covers all the content that I want to talk about in this tutorial. But again, this is really just the bare bones of chapter 2. If you really want to develop a deeper understanding, I highly recommend going over the lecture again, going over the tutorial again, and reading through the textbook and everything that the textbook has to provide. So section 1 was on sample spaces. And a sample space is a set of elements that correspond to the outcomes of an experiment. Sample spaces are great for representing, we can represent a sample space a lot more like with a diagram, and this can be very useful. Section 2 is on events. An event is a subset of sample space. De Morgan's laws are very useful, and we learned that in section 2. It's a very useful tool for solving questions, and one of the results was that for any event A, the union of A and A complement is omega. Section 3 is on probability. The definition of probability function, it's important to know what that is, including the infinite version. And we also learned about the union rule, which was another useful tool for understanding questions. And then we also have the additive property result, which was the probability of A complement is equal to 1 minus the probability of A for any event A. And so this formula is very important. Like, I still use this formula today, even through like way throughout undergrad. And it's very useful because you can go from probability of A to the probability of A complement, or the probability of A complement to the probability of A very easily. And finally, section 4 was on the products of sample spaces. And we say that for any two sample spaces, omega A and omega B, the combined sample space of omega AB is all the pairs from the sample spaces A and B. And then when it comes to infinite sample spaces, this occurs when the number of outcomes is infinite. So that concludes the tutorial. I hope you guys enjoyed it. Hopefully that helped clear up any confusion and assisted with understanding chapter 2. But if you still have any questions, feel free to post them on Piazza, and or send me an email at steven.brock@mail.utoronto.ca, and I'll always have office hours on Wednesdays from 3 to 4 p.m. Eastern Time. Thank you very much, and best of luck with your studies.